let's have a look at this question. So here we are given aqueous solution of HNO3, KOH, CH3COH and CH3CONA, and they are of identical concentrations. And we have to find out the pair out of these four, the combination, a pair which will result in a buffer solution. Now, what is a buffer solution, or what are the parameters, conditions for a solution to be buffer? Well, there are two types of buffer. First one we can say is the acidic buffer, which is the combination of weak acid, a mixture of weak acid and its conjugate base, right? And another one is what? Another one is the basic buffer, which is the combination of weak base plus its conjugate acid. Let's do a quick revision here. What do we mean by conjugate acid and conjugate base, right? So if HA is a weak acid, what do we mean by weak acid? Well, it will not dissociate completely, right? There will be partial dissociation, which is reversible reaction, right? That's what we denote here. And we'll get H plus ions and A minus ions, and these all are in aqueous solution. Okay, so here when HA is a weak acid, it dissociates to give H plus ions. So A minus, right, the negative part, that is called as conjugate base. Similarly, what would be conjugate acid? Well, let's say if we have BOH, right, a weak base, it will dissociate partially, or I would say dissociate, partial dissociation would happen, and we'll get what? We'll get OH minus ions plus B plus, right? This is all in aqueous medium. So here the positive part, the B plus, that is called as what? Conjugate acid, right? So after knowing all this, what has been given to us is the four aqueous solutions, which is KOH, we have HNO3, we have CH3COOH, and we have CH3COONA, right? So which pair will give us the buffer? And we have to find, it would either be one of these two pairs, one of these two combinations. The pairs have to be one of these two combinations. So what about KOH? Well, KOH is a strong base. It dissociates completely, right, to give K plus ions and OH minus ions. So obviously KOH is not in the criteria. What about HNO3? Well, HNO3 is also a strong acid. It totally dissociates to give H plus ions and NO3 minus ions. So even HNO3 does not fit our criteria. What about CH3COH? Well, CH3COH, acetic acid, is a weak acid, and it dissociates to give what? CH3CO minus plus H plus ions, right? All in aqueous medium. Okay, so here what is our conjugate base? We know CH3CO minus is our conjugate base, right? So we have weak acid with us. So we need another solution which will give us conjugate base, right? So the conjugate base, which is what? Which is CH3CO minus. Okay, next we have is CH3COONA. Well, this is a salt which will dissociate completely to give CH3CO minus plus Na plus, and these all are in aqueous medium, right? So see the combination, the combination of these two. CH3COH is what? Is a weak acid, which we wanted. CH3CONA is what? It's a salt of weak acid, and on dissociating in the aqueous medium, it is giving us CH3CO minus, which is the conjugate base of CH3COH. That's what we wanted, right? So this is what? This is the combination which contains a weak acid and another solution which is giving conjugate base in this aqueous solution, right? So the combination that will give us a buffer would be what? Would be CH3COH plus CH3CONA. And which option here? Well, it is our option D, which is the correct option. However, let's go through all these three options and let's find out if we are not missing out on anything, right? So the first option is HNO3 and CH3COH. So we have a weak acid, however, we do not have its conjugate base, right? Why? Because HNO3 will dissociate completely to give H plus ions NO3 and NO3 minus ions. So obviously, option A is not correct. What about KOH and CH3CONA? Well, KOH is a strong base, right? It will dissociate to give what? K plus ions, OH minus ions, right? And CH3CONA is a salt of weak acid and it will give us CH3CO minus ions and Na plus ions in the aqueous medium. So it does not fit our criteria. We do not have weak acid among us. So option B is also not correct. What about option C? Well, option C is also kind of same. Why? Because HNO3 is strong acid, which will give us H plus ions and NO3 minus ions. And CH3CONA will give us CH3CO minus and Na plus. Right, so we have strong acid in this option, but not a weak acid that we wanted. So that's why option C is also not correct. And the correct option to this question is option D. Let's have a look at this question. So here we are given two aqueous solutions. One is acetic acid, another is sodium acetate. And we are mixing them and diluting it to 100 ml. Right, and we have been given pKa of CH3COH, which is the acetic acid, as 4.76, and we have to find the pH of the buffer solution so formed. Well, it's an example of which buffer? I hope you remember this is an example, or this is a criteria of acidic buffer. It's a combination of weak acid, which is what? Which is CH3COH in this case, and its conjugate base, which is given by what? Which is given by CH3CONA. Right, so this is a salt of weak acid which will dissociate completely to give CH3CO minus plus Na plus. This all is there in the aqueous medium. Right, so what do we have here? We have a weak acid in combination with, or as a part of mixture with its conjugate base, which is CH3CO minus, right? So this is an example, classic example of acidic buffer. And we have to find out the pH of this acidic buffer. What do we know? Well, through the Henderson equation. I hope you remember the formula, right? It's the pH of the acidic buffer or a buffer solution is given by pKa plus log of concentration of salt. Here we are talking about the salt of the weak acid, right? The sodium acetate divided by the concentration of the acid, which is what? Acetic acid in this case, the weak acid, right? So we have to find the concentration of the salt and acid, and we'll just have to put the values. Why? Because we already know that the value of pKa is 4.76. That has been given to us, right? For acetic acid. Okay, so we have been given 10 ml and 1 molar solution of acetic acid, 20 ml and 0.5 molar solution of sodium acetate. Okay, let's see what the concentration would be. Well, let me write it here. CH3COH is what? It is 1 molar and 10 ml, and CH3CONA, right? That is 0.5 molar and 20 ml. Let me just cross check once. I've not made any mistake. Yes, I've not. Okay, so what would be the number of millimoles? Since the volume is in milliliters, we'll get the number of millimoles here, right? So the number of millimoles of CH3COH would be 10 into 1. That is 10 millimoles. Okay. What about CH3CONA? What I've done here is just multiply molarity into volume, right? Because we know molarity is what? Molarity is number of moles per unit volume. So number of moles will be molarity into volume. That's what I've done here. So for CH3CONA, which is acetic acid, we'll do the same. 0.5 into 20, that will also be 10 millimoles, right? So in the solution, when we have mixed them, the number of millimoles of CH3COH, acetic acid, is 10. And number of millimoles of CH3CONA is also 10. But what is the volume? Because we need the concentration, right? So concentration would be number of moles divided by volume. Right. In the question, it has been given that the solution after mixing was diluted to 100 ml. So the total solution of the volume is 100 ml. Right. Now we can easily calculate the concentration. So what would be the concentration of the salt? Well, it will be 10 millimoles divided by 100. Right. That is also in milliliters. So we are good here. Also for CH3COH, it will be 10 divided by 100. Right. So now let's put these values in the equation or the formula that we have, and we'll get our answer. Okay. So what is the value of pKa? Well, pKa is given to us as 4.76 for CH3COH, right? pKa will be for weak acid. What about the concentration of salt? Well, the concentration of salt is 10 divided by 100, right? And what is the concentration of acid? That is also 10 divided by 100, right? The 100 will go in the numerator. So this all cancels out. Log 1 is what? Right? This will become 1. So log 1 is 0. So all of this becomes what? Equal to 0. And what is the pH that we get? That is 4.76. Let's see which option does it match. Well, it matches our option B, which is the correct option. Let's have a look at this question. So here we have a reaction vessel in which this equilibrium is set up. SO2Cl2 gaseous in gaseous form. It dissociates to give SO2 gas plus Cl2 gas. Right. And we have been given that for the reaction mixture, we increase the volume. Right. And then the equilibrium was re-established, and we have to find what would have happened out of these 4 options. Right. Well, this is a case for what? Le Chatelier's principle. Right. So we had an equilibrium established, we changed some parameter, and then the equilibrium was re-established again. So since we have been given an equation, let's see. SO2Cl2 gas will dissociate to give SO2 gas, all in equilibrium with SO2 gas and Cl2 gas. Right. Okay. So this is, let's imagine right now the equilibrium is established and we have just increased the volume. What would happen? Well, the pressure will decrease. Why? Well, we know PV is equal to nRT, right? And if everything else is constant, nRT, we are considering the temperature is constant, right? So pressure is inversely proportional to volume. Right. So if the volume is increasing, the pressure will decrease. Right. Now, since the pressure will decrease, now the system, the vessel, the reaction vessel, it will not be at equilibrium. Right. It will try to achieve its, the lower energy point, which will be the equilibrium point. Right. So what would it do? Well, according to Le Chatelier's principle, the pressure has decreased now. Hence, it will try to re-achieve its pressure value. Right. And how would it do that? Well, to increase the pressure of the system, the reaction will have to go to the forward direction. Why? Well, in the forward direction, you can see the number of moles are increasing. The number of moles of gaseous components, right? So, as the number of moles of gaseous component will increase, the pressure of the system will also increase, right? How do we know that? After we have established, we have already doubled the volume. So, now the volume has become constant and temperature is also constant. So, we know that pressure is directly proportional to number of moles. So if number of moles are increasing, the gaseous number of moles, hence the pressure will also increase, right? So when we change that equilibrium, when we change the conditions, right, the equilibrium was disturbed and pressure decreased. Now the equilibrium, the reaction will move in that direction so as to re-achieve that equilibrium. That will be in the forward direction, right? And hence it will re-achieve its equilibrium. So let's see the options that has been given to us. So the first one says the amount of SO2 will have decreased, right, after the equilibrium was re-established. Well, for equilibrium to re-establish, the reaction will move in the forward direction. If the reaction is moving in the forward direction, then the amount of SO2 gas will increase. It will not decrease, right? Hence, option A is not correct. What about option B? The amount of SO2Cl2 will have increased. No, if the reaction is moving in forward direction, hence more of SO2Cl2 will dissociate. So the amount of SO2Cl2 gas will actually decrease and not increase. So option B is also not correct. What about option C? The amount of Cl2 will have increased. Let's see. Well, if the reaction is moving in forward direction, yes, the amount of Cl2 will increase. Yes, this is correct. Let's have a look at option D also. It says the amount of Cl2 will have remained unchanged. Well, absolutely not. It would have remained unchanged if the number of moles on the gaseous moles on the reactant side would have been equal to number of gaseous moles on the product side. If it would have been that case, then option D would have been correct. But it's not the case. We have more number of moles or more number of gaseous moles on the product side as compared to the reactant side. Hence, we can say for sure that option D is not correct. So, the correct option is option C. Let's have a look at this question. So, here we have to find an organic compound which has the molecular formula C9H18. Right. So, other conditions that are given to us as that all carbon atoms are sp3 hybridized and it's all hydrogen atoms are identical. Right. So, we have to find a compound, an organic compound which satisfies, or which I would say, follows all these three criteria that are given to us, or I would say the conditions that are given to us. So, its molecular formula should be C9H18, all S carbon should be sp3 hybridized and all hydrogen atoms are identical. Let's have a look at the four options or the four organic compounds that are given to us. Okay, so the first one, right, let's first find out if its molecular formula is correct. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbon atoms. Correct. How many hydrogen atoms? 3 plus 2, 5, 1, 6, plus 3, 9, 2, 11, 12, 13, 15, 3, 18. Okay, so C9H18. So the first criteria is filled. Next it says all the carbon atoms should be sp3 hybridized. Well, as we can see here in this A compound, organic compound, right? All the carbon atoms are making sigma bonds, right? Then all the carbon atoms are making 4 sigma bonds. Each carbon atom, I would say. Hence, yes, all the carbon atoms are sp3 hybridized. Right. What about all the hydrogen atoms being identical? Right. How do we find that? Well, that is the criteria which is not true for this first option. Why? Let's see. Okay. So, these 3 hydrogen atoms, these 3 hydrogen atoms and these 3 hydrogen atoms, right? If we count this 3-member ring as one unit, we can see that these 9 hydrogen atoms are identical. Yes. But they are not same as these 6 hydrogen atoms. These 6 hydrogen atoms, right? These 6 hydrogen atoms, they are very different. They are not identical to these 9 hydrogen atoms. I've circled out the whole CH3, but I'm talking about just the hydrogen atoms here, right? So since here we can see we actually have 3 types. These hydrogen atoms are same, right? So we have 3 types of hydrogen atoms in this compound. Hence, option A is not correct. Let's have a look at option B. Okay, so how many carbon atoms? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. So it follows C9. What about hydrogen atoms? Let's have a look at that also. So 3 plus 6, 3 plus 3, 6, plus 3, 9, plus 3, 12, plus 3, 15, plus 3, 18. So we have C9H18. Okay. What about the hybridization? Well, we can see that all carbon atoms, they are making 4 sigma bonds, right? Each carbon atom is making 4 sigma bonds. So all the carbon atoms are sp3 hybridized. So that's also correct. Okay. What about the hydrogen atoms being identical? Okay. So if you see this as one unit, right? So all these hydrogen atoms which are attached to, which are part of this methyl group, right? All these methyl groups are actually identical. Right. So that makes all the hydrogen atoms identical. So yes, all the hydrogen atoms in this molecule are identical. They have the same environment. Right. So option B is correct. Let's have a look at option C and D also. Okay, so option C, how many carbon atoms do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, okay, we have C9. Sorry, C9. What about hydrogen atoms? Let's check. 3 plus 3, 6, plus 3, 9, plus 3, 12, plus 3, 15. We have 16 here, 17 here, right? And we have 18 here. So we do have C9H18. Okay, what about hydrogen atoms? Sorry, what about hybridization? Well, all the carbon atoms are making sigma bonds, right? Each carbon atom is making 4 sigma bonds, and that makes it all the hybridization of all carbon atoms as sp3. What about, let me clean it up. What about the hydrogen atoms? What about the hydrogen atoms? Well, let's have a look. So, hydrogen atoms are actually not identical, right? Here, the hydrogen atoms are directly attached to the carbon which is there in the ring. However, we have hydrogen atoms attached to CH3 being part of the methyl group as well, right? So, hence, option C does not have all the hydrogens, all the identical hydrogen atoms. So, option C is also not correct. What about option D? So, let's count number of carbon atoms. 1, 2, 3, 4, 5, 6, 7, 8 and 9. C9. Okay, what about hydrogen atoms? 3, 3, 3. So, we have total 9 here. 10, 11, 12, 13, 14, 15, 16, 17 and 18. You have 18 hydrogen atoms. So, that is correct. What about hybridization? Well, we can see that all carbon atoms are making sigma bonds or single bonds, right? So each carbon atom is making 4 sigma bonds. That makes the hybridization of all carbon atoms as sp3. What about the hydrogen atoms? Well, if you have a closer look, you can see that these three and these three, right? These total 9 are one type of hydrogen atoms, right? These 6 are one type of hydrogen atoms, and these 3, which are directly attached to the ring, the hexagon ring, right? We have these which are attached to hexagon ring, and the carbon also had methyl group attached to them, right? So these 3 are identical, right? So we have total 3 type of hydrogen atoms in this option D, and which is what we don't want. We only wanted all the hydrogen atoms to be identical. So option D is also not correct. So the correct option to this question is option B. Let's have a look at this question. So here we have to find out the work done in a cyclic process. Right. So, from first law of thermodynamics, we know that the change in internal energy is given by Q plus W. Right. So, in a cyclic process, what would be the value of delta U? Well, we know that internal energy is a state function. Right. Its value depends upon the initial and the final conditions. It does not depend, the value of internal energy does not depend upon the path taken. And for a cyclic process, we know that the initial value will be equal to final value, right? Okay, so if initial value is equal to final value, that makes delta U as 0, right? So delta U will be what? Delta U will be initial value of the internal energy value at the final stage minus the internal energy value at initial stage. And since its values are going to be equal, since it's a cyclic process, that makes delta U as 0. Always remember that the value of state function for a cyclic process will be 0, right? So delta U will be 0. Hence, what would happen? So Q plus W is equal to 0. So what would be the work done? Work done will be minus Q, minus heat, right? So which option does it match? Well, we can see here it matches option D, which is the correct option.